So hello guys, let's continue with the remaining sums. So given the following data for incident wavelength and the stopping potential obtained from an experiment on photoelectric effect, estimate the value of Planck's constant and the work function of a cathode material. What is the threshold frequency and corresponding wavelength? What is the most likely metal used for emitter? So here we have given two incident wavelength and corresponding to that two stopping potential. So let's write lambda 1 as 2.536 into 10 raised to minus 7 meter obviously, and lambda 2 as 3.65 into 10 raised to minus 7 meter. Similarly, corresponding to them, the stopping potential V naught 1 equal to 1.95 volt and V naught 2 equal to 0.5 volt. So the Einstein photoelectric equation for both of them will E V naught 1 equal to hc by lambda minus work function, and E V naught 2 equal to hc by lambda, here lambda 1, here lambda 2, minus work function. Now subtract both the equation, we get E V naught 1 minus V naught 2 equal to hc common lam sorry 1 by lambda 1 minus 1 by lambda 2. So V01 minus V02 equal to hc by E 1 by lambda 1 minus 1 by lambda 2. So now let's substitute the value of this in this equation. V01 is 1.95 minus V02 is 0.5 equal to H. C is 3 into 10 raised to 8 meter per second, and this is 1.6 into 10 raised to minus 19 into 1 by lambda 1. Lambda 1 is 2.536 into 10 raised to minus 7 minus 1 by lambda 2, 3.65 into 10 raised to minus 7. Now if you look carefully, here 10 raised to minus 7 and 10 raised to minus 7 are common. If I take it outside and put it in the numerator, this thing becomes h into, and subtracting this thing we get 1.45 equal to h into 3 into 10 raised to 8 plus 7, 15 divided by 1.6 into 10 raised to minus 19, and inside here 1 by, let me write the answer directly, 1 divided by 2.56 will become 0.394 minus 0.274. Solving this, we can evaluate h as 1.45 into 3 into 10 raised to 15 divided by 1.6 into 10 raised to minus 19 will give us 1.875 into 10 raised to 34, and this value will become 0.12, and solving this we get the value of Planck's constant as 6.44 into 10 raised to minus 34 joules second. Now the second part of the question wants us to know the threshold frequency and the corresponding wavelength. Also, what's the most likely metal used for emitter? So let's evaluate that. So let's calculate the work function. So for any given data, for any one of the given data, we can write the work function as h nu minus ke max, or more precisely h nu minus e v naught for any value of stopping potential. So we know h, we know v is nu is c by lambda minus e v naught. Substitute all the values, 6.44 into 10 raised to minus 34 into 3 into 10 raised to 8 divided by lambda. Let's take this value of lambda for this stopping potential. So lambda will be 2.536 into 10 raised to minus 7 minus 1.6 into 10 raised to minus 19 into 1.95, which implies our work function will become 1.932 into 10 raised to minus 25 divided by 2.536 into 10 raised to minus 7 minus 1.6 into 10 raised to minus 19. So 1.6 into 3.12 into 10 raised to minus 19. So let's solve this and we get work function as, so solving this we get work function as 4.498 into 10 raised to minus 19. So in terms of electron volt, we get work function as 2.81 electron volt. Now let's evaluate the threshold, frequency and corresponding wavelength. So our work function was 4.49 into 10 raised to minus 19 joules. So we know work function is h nu naught, which implies nu naught is work function by h, that is 4.49 into 10 raised to minus 19 divided by 6.64 into 10 raised to minus 34, which comes out to be 6.76 into 10 raised to 14 hertz. Now the corresponding wavelength, you know, C equal to mu naught lambda naught, which implies lambda naught equal to C by mu naught, that is 3 into 10 raised to 8 divided by 6.76 into 10 raised to 14. This gives us the value as 4.43 into 10 raised to minus 7 meter, or to write it in Armstrong, 4430 Armstrong. So let's look at the next sum. Calculate the wavelength associated with an electron, its momentum and speed when it is accelerated to a potential of 54 volts, and second part is when it is moving with kinetic energy 150 electron volt. So wavelength associated with an electron, its momentum and speed. So let's first calculate the wavelength. So for a wavelength of an electron accelerated through a potential, it is given as lambda equal to 1.228 into 10 raised to minus 9 divided by root under v. So 1.228 into 10 raised to minus 9 divided by root under 54. Solving this, we get 0.167 into 10 raised to minus 9 meter, that which implies lambda is 1.67 into 1.67 Armstrong. Now from de Broglie's hypothesis we know lambda equal to h upon p, which implies momentum p will be h upon lambda, that is 6.63 into 10 raised to minus 34 divided by lambda is what we got, 1.67 into 10 raised to minus 10. So solving this we get value of p as 39.70 into 10 raised to minus 25 kg meter per second. For the next part we have been given the kinetic energy. So the kinetic energy is 150 electron volt. To convert it into joules, 150 into 1.6 into 10 raised to minus 19 joules. We need to find out the wavelength associated with the electron. So we know kinetic energy. Let's find out the momentum. momentum P is given as root under 2m kinetic energy. So that can be written as 2 into mass of electron is 9.1 into 10 raised to minus 31 kgs into kinetic energy, that is 150 into 1.6 into 10 raised to minus 19. So solving this, the value of momentum as 6.609 into 10 raised to minus 24 kg meter per second. So we know lambda by de Broglie's hypothesis is given as lambda is equal to h upon p. Therefore 6.63 into 10 raised to minus 34 divided by 6.609 into 10 raised to minus 24. This can give 1.003 into 10 raised to minus 10 meter. One more thing we need to find out is the speed for both the cases. So for the first case, the momentum that we got was 39.70 into 10 raised to minus 25 kg meter per second. So we know P equal to mv, which implies V will be equal to P by m. Therefore 39.70 into 10 raised to minus 25 divided by mass of electron is 9.1 into 10 raised to minus 31 kg. So which implies we get the value of V as 4.36 into 10 raised to 6 meter per second. So for the second case now, the momentum that we got was P equal to 6.613 into 10 raised to minus 24 kg meter per second. Similarly, for this, the value of V will get as 7.26 into 10 raised to 6 meter per second. Let's look at the next sum. The de Broglie wavelength associated with an electron and proton are same. What will be the ratio of their momenta, their kinetic energy? So they have given that lambda p is equal to lambda e. From de Broglie's hypothesis we know that lambda is h upon p. So for proton, lambda p will be h upon momentum of proton, and similarly lambda e will be h upon momentum of electron. So h cancel. We need to find out the ratios of the momenta of electron and proton. Therefore Pe by P will be 1:1. They are equal. Second, we need to find out the kinetic energy. Now we know that kinetic energy can be written in terms of momentum as P square by 2m, or momentum can be written in terms of kinetic energy as 2m P equal to 2m kinetic energy. Therefore from this ratio we can write as 2m E kinetic energy of electron divided by 2mp kinetic energy of proton is equal to 1:1. Now 2 gets cancelled. We know mp is equal to 1836 times me. So substituting this, let's see further what we get. So we had root under me ke by mp kp 1:1. Now taking square root we get meke equal to mp kp, and as we discussed for before, mp equal to 1836 into me. Therefore me ke will be 1836 times me kp. So me cancel, ke by kep will be 1836:1. which can also be written as 1 in 36 ratio 1. So let's see the next sum. Two particles have the same de Broglie wavelength and one is moving 4 times as fast as the other. If the slower particle is an alpha particle, what is the possibilities for the other particle? So both the particles have the same de Broglie wavelength and velocity of one is 4 times the velocity of other. So let v1 be 4 times v2. Okay, so if the slower particle is an alpha particle, so out of v1 and v2, our alpha particle will be the second particle. Therefore two particles have the same de Broglie's wavelength. There lambda 1 equal to lambda 2. Therefore h upon p1 is equal to h upon p2. H upon m1 v1 is equal to 1 upon m2 v2. This implies m1 v1 is equal to m2 v2. Now v1 is 4 times v2. This implies m1 by m2 is equal to 1 by 4. That is 1 ratio 4. So we know for an alpha particle, its mass is 4 atomic mass unit. So obviously for the other particle, its mass will be 1 atomic mass unit. And the particles corresponding to this mass are protons or neutrons. What is the speed of proton having de Broglie wavelength of 0.08 Armstrong? So we know from de Broglie's hypothesis lambda equal to h upon p or p equal to h by lambda, and p is mv equal to h by lambda. So v equal to h by m lambda. So substituting the values, h equal to 6.63 into 10 raised to minus 34 joule second, and mass of proton is 1.67 into 10 raised to minus 27 into wavelength is 0.08 Armstrong. Now 0.08 Armstrong can be written as 0.08 into 10 raised to minus 10 meter. So this things becomes 8 into 10 raised to minus 12 meters. So solving this, the value of v which we get as 4.957 into 10 raised to 4 meter per second. Pretty easy sums. Let's look at the next one. In a nuclear reactor, neutrons travel with energies of 5 into 10 raised to minus 21 joules. Find the speed and wavelength. So we need to find the speed and wavelength. Kinetic energy is given as 5 into 10 raised to minus 21 joules. We know kinetic energy is half mv square, which implies v will be 2 ke by m under root square. So which implies 2 into kinetic energy is 5 into 10 raised to minus 21 upon mass of neutron is almost equal to mass of proton, that is 1.67 into 10 raised to minus 27. So solving this, we get v as 2.43 into 10 raised to 3 meter per second. Now the corresponding wavelength can be given by de Broglie's hypothesis as lambda equal to h upon p, h upon mv. Therefore 6.63 into 10 raised to minus 34 divided by mass of neutron is 1.67 into 10 raised to minus 27 into velocity 2.43 into 10 raised to 3. So solving this, we get lambda as 1.62 into 10 raised to minus 10 meter, or 1.62 Armstrong. Let's look at the last sum of this chapter. The ratio of de Broglie's wavelength of an electron and a proton when both are moving with the same speed. So first case A, VE equal to VP. So lambda P is equal to H upon MEVE, sorry, MPVP, and lambda E equal to H upon MEVE. So the ratios will be lambda E upon lambda P, H will get cancelled, MPVP upon MEVE. We know VE is equal to VP, so these two things will get cancelled. So the ratio of their wavelengths are inversely proportional to their masses. Second thing we need to find is their ratio if the energies are same, that is same kinetic energy, which implies Ke of electron is Ke of proton. So momentums will be momentum of electron 2m Ke E, and momentum of proton 2mp Kep. So solving this, lambda E by lambda P will be root under, obviously proton momentum will be up and electron momentum will be in the denominator, 2mp Kep upon 2me Ke E. 2 cancel. We know Ke of electron and kinetic energy of proton are same, so these two things will be also cancelled. Now our ratios of wavelength are roots of their masses, mass of proton. Let's see the third case when momentums are same. Obviously lambda P is H upon P, and lambda E is H upon momentum of electron. When PE is equal to PP, that is momentum of proton is equal to momentum of electron, lambda E upon lambda P will be equal to PP upon PE, that is 1:1, that are equal. The wavelengths will be equal.